This method by washers is an alternate method to using discs. Now, this is very important that when we are doing our volumes, that when we understand what the cross-sectional area is going to look like. So when we slice it and we have a disc, we're going to use the formula for a circle. If we slice it and our cross-sectional area is a washer, we need to find that red area in here. And it's important to recognize that we do not, and I'm going to repeat, we don't use the difference in the two radiuses. So for example, if I do radius, the big radius of the outside circle minus the radius of the inside circle, and I take this and I square this, okay, there's a problem with that because when I take the difference of the two radiuses, what I'm finding is this length in here. Okay, and if I square that, I'm going to find, and you multiply by pi, I'm finding the area of that circle. Well, that circle doesn't really have anything to do with the red washer area that I want. So instead of doing that, what we're going to do is to find the area of the washer, we're going to use pi r squared for the big circle. And then we're going to subtract r squared, pi r squared for the small circle. And then we're going to factor that out. So if I do the difference in the radius is squared times pi, this is different and it does not work for this red area of the washer. If we take the difference of the squares of the radiuses, and then multiply by pi, this will find the red area. So I'm just going to highlight that in red because this will calculate that red area. We're looking for the difference in the areas of the two circles. We are not looking for the differences in the radiuses because the difference in the radiuses do not give us that area. Okay, so in this problem here, we are rotating this parabola with an outside edge at x equals 2, and we're rotating that around the y-axis. So the volume that we generate, we're going to slice it along the y-axis. Okay, so perpendicular to the y-axis, and our cross-sectional area are going to be washers. So we're going to find the area of these washers. The key is finding the areas of the cross-section. So if you want to imagine what this shape looks like, it's going to look like this. We have our parabola. It's going to be rotated around the y-axis, and it's going to kind of half rotated the shape, the 3D volume around. So you can kind of see there's an inside cup that is a parabolic shape, and then there's the outside cylinder, and in the red there, you can kind of see one layer of a washer slice. And we're going to give that washer slice a thickness of dy to integrate this. Okay, so again, the key is the first thing we need to do is determine the cross-sectional area. Is it a circle or is it a washer? And we have to be aware of when we are using what. If we have a washer, we need an equation that calculates the outside edge. Okay, so we need the outside radius. So I'm going to write here the area of our washer is going to be equal to, well, we're going to take our outside edge, the big R squared, and then we're going to subtract the inside edge, little r squared, and then we're going to multiply that by pi. In this particular example here, the outside edge is going to be determined by this length here. Okay, so the circle that's going to be generated is going to be this length here, so it's going to be 2 squared. Okay, and if I take a look at my diagram here, that blue line represents the outside edge, and that length is 2, and it's constant. It doesn't change. The inside edge, however, when we take a look at the slice of the washer, is going to be this distance in here. Okay, so it's going to be our little radius. Okay, that little radius is going to be determined by the x value. So this is going to be this length here, we're going to say is x, and we need to express that in terms of y. So if y equals x squared, we're going to say that the function then is x equals plus minus square root y, and then that's going to allow us to use our dy. So this is going to be equal to root y, and we're going to square that radius. So it's going to be minus the small radius squared, and the small radius is going to be determined by root y. And that's, if I multiply that all by pi, we're going to end up with our cross-sectional area. And that's the key to finding these volumes. Once we have the cross-sectional area, our volume can be generated by, we're going to integrate the area of 2 squared minus root y squared. We're going to times that by pi. We're going to give it a thickness of dy, and we're going to integrate this from y equals 0. So we're going to start at the bottom here at y equals 0, and we're going to do that all the way up until y equals, where it intersects x equals 2 is going to be y equals 4. So our integral is going to be from 0 to 4. Now at this point we can easily anti-differentiate this and work out the volume. So we end up with 4y minus y squared over 2. And then we're going to give it bounds from 0 to 4. And then typing that all in, we're going to end up with 16 minus 16 over 2, which is 8. Minus, when we plug 0 in, we get 0. So the volume of this works out to be 8 pi units cubed. Okay, so that volume of that shape that we get by rotating that parabola and then outside edge of x equals 2, we're going to end up with a volume of 8 pi.